Okay, today we will keep today's class short. So, like in the last class, we were considering about image fusions from multiple sources. So we considered several papers in which they have different source types of input images. Some of them may be hyperspectral images, which are like low resolution but obtained over a large number of wavelengths, and there are some multispectral images or maybe some panchromatic or RGB images which may have which is captured from only one wavelength, but it's of a higher spatial resolution. So then how to create an image which combines both the two, that is how can we get a high resolution image at multiple wavelengths. So that like we saw several papers related to that, several that is on related versions of this problem. Now, using somewhat similar ideas, we today we will discuss some other works where we are trying to estimate certain physical or atmospheric variables from these remote sensing sources, and there might be multiple sources, and how we can reconcile the observations from the different sources. So in general, today we'll be talking about proxy measurements. So proxy measurement, the idea is that suppose you want to measure certain geophysical quantities, let us say rainfall or temperature or wind speed at very high altitudes and things like that. Now these are things there are certain variables which are difficult to measure directly. Like rainfall might be measured using rain gauges, but then there are regions where setting up rain gauges is difficult. And besides, rainfall also varies spatially, and and it is not possible to build such a dense system of rain gauges such that we will be able to capture the requisite spatial variability. On the other hand, rainfall at least is still possible to measure directly by rain gauges. But say suppose you want to measure something like say wind speed which is 500, let us say 2 kilometer above the Earth's surface. So these are much more difficult to measure directly. So what is usually done in such situations is that we have satellite imagery or remote sensing imagery. Now those imagery, they such images can be captured, of course, as at different wavelengths, or maybe at a dense range of wavelengths. That's what is known as the hyperspectral images, as we considered yesterday. So the idea is that when we have such remote sensing imagery, we like some so those things or those imagery, they do not contain the value of any variable per se, but whatever is captured in those images may be mapped to the values of different variables of interest. That is, so say suppose I have captured the like a satellite imagery over a particular region spanning a particular spatial regions. Now at every pixel of those remotely sensed images. So let us say that let us say like this is my just a remote sensing image. So each of these pixels, they will have some value, some pixel value. Let us say like xi comma j. Now, what this xi comma j is, that of course depends on that is basically the intensity of the image in the wavelength being considered. Like if it were a normal image like RGB image, then this would simply mean the intensity of the pixel, some value between 0 and 255 in the visual range. So if it appears black to us, then it will be 0. If it is white to us, it will be 255, and if it is something in between black and white, it will be somewhere like some intermediate value. Similarly, like from that is of course for a monochromatic RGB, I mean the grayscale image. If we go for RGB, then also like these pixels will take some value between 0 and 255. So if it is the R channel, then 0 will mean like black, and 255 will mean red, like deep red. If it is a similarly, if it is the green channel, then 255 will mean a deep green, and so on. So like it depends on whichever wavelength the image is being captured. Now these pixels are actual, like in case of remote sensing images that are captured over a spatial region, these pixels are actually the actually correspond to some spatial locations, right? Like in the last few classes we have been repeatedly talking about like the or what is the size of each pixel. Like we came across situations like when one pixel may be say 15 meters or 100 meters or something like that. So basically each pixel is a spatial block, is a spatial region, say 15 meter by 15 meter or 100 meter by 100 meter spatial region. And suppose I'm interested in a particular geophysical variable, which I may define it by y. So that also variable may also be measured at these different small blocks or small regions. Of course, like these are like ideally we should go for point measurements, but let us say that the blocks are small enough so that like they are that is the point measurements within the block can all be approximated by a single value which is characteristic of the block. So xij is the pixel intensity value, and let us say yij is the value of a particular physical variable which is of interest to us at that same location. So then what I really want is I want to predict this value of yij, or I want to estimate it. So what I do is I learn some function like this, right, which maps the pixel intensities into the into the geophysical value which I am interested in. And this function f is like best parameterized with the help of a neural network. And in fact we can also like relax this kind of this that is by bringing it or by allowing special effects. So instead of considering the mapping to be from one pixel to another, I can as well like consider take the input to be this whole image X, and the output to be the whole spatial distribution of the variable which I am interested in. Okay, so this is like per pixel. Here the mapping is being done per pixel, and here the mapping is being done like it considers the spatial influence. Right, so this is what we get. So the target in this case is to learn some kind of a neural network which maps from like these kinds of images to the variable which I am interested in. Now, there might be these kinds of images might be obtained from different sources. So, like for example, there can be like ground radars, there can be these measurements from satellites, there might be measurements from aerial radars, etc. So each of them will have their own axes, but the and from each of those axes, let us say I have x1, x2 up to xk from k different sources, and then I have to like utilize all of them to get a single y, which is the variable of my interest. So I have to that is so let us say I build a model f1 which predicts y from x1. Let us say f1 x1. But then similarly for x2 I will need a different model, let us say f2 x2 and so on. So basically we will get an ensemble of different models, and so I will somehow have to utilize these different models to make the to estimate the y, and these models may have different discrepancies, or they may disagree among like what the value should be here at this location or at this location. So then we'll have basically, when we have so many different models, we can will actually have to take the that is takes, like basically it's a case of an ensemble model. So those of you who are familiar with machine learning ensemble methods in machine learning, let us say a random forest or AdaBoost or things like that, you know that you have a say an ensemble of models like this, and each of which may give some estimate of the geophysical variable at the different locations. So I will have to take a weighted vote of all of them, and then there the way, so that for which I need to basically determine the different weights of which they should have. So uh, what the papers which we are going to talk about today will help us to not to first of all you build neural networks for the different individual sources, but also find a way of reconciling the predictions for the from the different neural networks. Okay, so let us come to this work. So, as this says, the rainfall estimation from ground radar and TRMM precipitation radar using hybrid deep neural networks. So, as the name suggests that they are ground radar. So these are some rainfall measurement radars which are set up on the ground, and then there are there is a TRMM. So TRMM is the Tropical Rainfall Measuring Mission. So it's an satellite based project. It's a spaceborne project from which they try to measure the precipitation in the earth. So they have their airborne or spaceborne radars. So we have two different sources of information. So the y in this case is precipitation, rainfall at different locations, and it is being measured from two sources or two x. There are two sets of x's. One kind of one, or let us say x1 is coming from ground observations and x2 is coming from space observations. So let us see what this paper is saying. So remote sensing of precipitation is critical for regional, continental and global water and climatic research. That goes without saying. This study develops a deep learning mechanism to link between point-wise rain gauge measurements, ground-based and spaceborne radar reflectivity observations. Two neural network models are designed to construct a hybrid rainfall systems where the ground radar is used to bridge the scale gaps between rain gauge and satellites. Right. Two neural networks. So as I said, F1 and F2, they are designed to construct a hybrid rainfall system. Like one is the so there are different rain sources. The first so they want to build a different like two neural networks to reconcile the sources. The first model is trained for ground radar using rain gauge data as target levels. So the rain gauge data is something like our ground truth in this case, the actual values of y, right? And the so x1 is the ground radar like ground radar observations. Whereas the second model is for spaceborne tropical or TRMM precipitation radar using the ground radar estimates as the training levels. So there is so like let us say x1 is the, or okay, first let us say z or y, or sorry, y. This is the uh, rain gauge. So this is considered to be most authentic or the ground truth. Then comes X1, which is the ground radar. So basically, that is a model like F1 is trained, and like using these Y as the labels. And then there is a second model when the second model is for spaceborne tropical rainfall measure, or the TRMM precipitation radar using the ground radar estimates as the training levels. So in this case, like there is X2, which is the TRMM radar, and that is trained using X1 as the labels. So this is F2. Okay. So the data from 1 year of observations in Florida during 2009 is utilized to illustrate the applications of this hybrid rainfall system. Validation using independent data in 2009 as well as 2 year comparison against standard peer products demonstrate the promising performance and generality of this innovative rainfall algorithm. Right, so now let us come to the details of how they have proceeded. So let us come straight to the uh, okay, first let us look at the data set. So the data set is ground radar and rain gauge data is collected near Melbourne in Florida in the year 2009. In particular, the ground radar reflectivity measurements within 100 kilometers of a particular weather surveillance radar are considered. Now, uh, three rain gauge networks around the radar are utilized. So these rain gauge networks, these are considered as the most authentic source of information. So like these are the like, because these rain gauge is what it's something that measures the precipitation directly, unlike X the radars X1 X2 what they are measuring. So as I said, they measure like they basically capture images, and so those images are basically proxies for rainfall, but the rain gauge measures the precipitation directly. So then why not go for rain gauge only? That is why even talk about the radars. That is because like rain gauge is something that is a physical infrastructure that can be set up in one particular location, but radar image is something that can cover a larger region. So I cannot really go about setting rain gauges at every corner of the world. So I will have to use these radar images, which actually have a much larger range. That is, they can capture the images of a large region and then utilize those images to like somehow estimate the rainfall using the kind of functions F1, F2 that we are talking about now. So so this is about the ground based infrastructure. There are three rain gauge. There is one radar, one weather surveillance radar, and then that basically you can say it captures measurements of or rather it captures images of like 100 kilometer region around it. And then there are three rain gauge networks around that radar. These are also like these are the ground measurements. Now the TRMM PR data like from 542 coincident overpasses over the Melbourne region are collected, among which 74 cases have decent precipitation. So what this the 542, 74, etc. what it means is that the satellite, of course, is not stationary over that particular region. It like it is going in orbit. So there are only so in a given year, like in 365 days, let us say it this satellite, it crosses that particular region say 542 times. And now not all of those times will have any rainfall to report. So like they have the authors of this paper have manually identified some 74 of those passes which contain some significant amount of precipitation. Okay, and this is such radar observations are collected and are used to train the this model. So yeah, so this is the data source. Now coming to the methodology, let us come to the schematic diagram. So this is the schematic diagram. Yes, so like here what you are seeing is basically it's a, schematic diagram of the whole system. So there is so as you can see there is this ground radar, there is the T and that the TRMM, the airborne or spaceborne radar, and then there is this rainfall or the precipitation taking place. So both the ground radar as well as the TRMM radar, they there is a common region where both of them measure it. So this is taking like you can say that this radar is taking images of this block. Similarly, this spaceborne radar, this is also taking images of this block. And let us say that here we have a rain gauge which actually measures the quantity of the rainfall. So now, so this is like we can, as we said, this is our x1, this is our x2, and this is our y. Okay, now what is they are doing is that so here we have two blocks. One is the block 1 and the block 2. So the block 1, what it does is it has the ground radar and the target that is like the ground radar, whatever it is taken. So it is basically a profile view of the rainfall that it has captured, right? So like as you can understand, it, like it is that is the ground radar is here. It is taking like a sideways image like this. You can as they call it as a profile view. So that is so here is the input to this network is the profile view image captured by the ground radars, and the target corresponding target is the actual values of the precipitation in that region as obtained from the rain gauge measurements. So what is done is they use a neural network, especially MLP. MLP stands for multi-layer perceptron. So the multi-layer perceptron, which is a like a you can say a straightforward neural network. So using mostly fully connected layers. So the multi-layer perceptron is used to map these ground profile radars. I mean the ground profile observations from the radar to predict the rainfall values at the different locations. Now, so once this training is completed, we get a training model. Let's call it as the MLP1. So now like we get so once this model has been trained, this model like in the then like whenever we get new images from the ground radar, those images are passed through the or passed as inputs to the MLP1, which gives us the new these precipitation estimates. Now comes the second x2. So the like as you can see here, the observations are the is the vertical profile. So like the because the this spaceborne radar is above, so it is basically taking a vertical image of the region, while this was the horizontal image. So now these so now what we want to do is from these vertical profile images, I need to predict the values of the rainfall. Now, so for that, what is so what is the input we get from that? The input we get, sorry, I mean the what is the input level is this vertical profile imagery, and what are the outputs? The outputs, what they have done is that the MLP1 based rainfall estimates, which they have already trained from the ground based on the ground radar, they are the output levels. So the ground radar takes the images, the vertical these profile images. Those images are sent as inputs to MLP1. The MLP1 converts it into a map of rainfall, and then those maps of rainfall are like effectively the training labels for this MLP2, the second neural network. So the for the second neural network, the input is the vertical profile images from TRA from the spaceborne radar, and the output is the spatial map of the rainfall which they have got from MLP1. So this way, MLP2, the second neural network, which is also a multi-layer perceptron, that is also trained And like while it is being trained, the cross validation is done using the some standard TRMM products. So this TRMM, it is like it actually does TRMM already has a lot of data products where they provide high resolution estimates of rainfall all over the world. So they already have some kind of way to map their satellite imagery, or I mean their radar imagery to actual rainfall values. That is not done using deep learning, but using some other technology, let us say. Something which they have tried and tested. So on like while the ground truths in this case are coming from the MLP1, but before the but another source of ground truth is also coming from the standard TRMM products which were already available before this MLP1. So using these two sources of or ground truth, they are able to train this MLP2 model. So finally what happens is that we find that is we are able to get a system which takes observations from both the ground as well as the satellite and utilize them to make the estimate of the precipitation, uh, or a special map of the precipitation over the region. So what the rain gauges could have measured at only maybe a few locations, at those precise locations where the rain gauges are deployed, now we can, based on those, we can get a like estimate of the precipitation over the entire region. Okay, so the training of course requires the model parameter optimization. That is the standard process of deep learning, which most of you know anyway. So that they're like that is done through these back propagations. Now, if we come to the details of the two models, MLP1 and MLP2. So the first model, MLP1, it's just to recapitulate once again, its input at the radar, the ground radar observations, the training levels at the rain gauge measurements, and what it like once the model is trained, what it does is it like gives the spatial map of the rainfall based on the radar. And this is what the rainfall, I mean the model basically looks like. So it has the like, so these like you can say that these is a set of images they like which is obtained from the ground radar. So like we can say at different that is we can get at different altitudes we can get the measurements. And then there is a multi-layer or there are multiple hidden layers like this which take these images as the inputs, and then like these are all fully connected layers of a neural network. There can be like some particular number of such hidden layers which is not specified here, and then there is the output. Similarly, MLP2 has also has pretty much the same structure. So it's like input is the TRMM measurements from the TRMM radar. So once again, that's like a reflectivity profile of the radar, like at different altitudes and so on. And the inputs is like what is obtained from the ground radar. I mean yeah, so the inputs are obtained from the ground radar, passed through the MLP1, and then passed on as the ground truth spatial map of the rainfall. And apart from it, there are also the rainfall estimates which are obtained from the TRMM data products. So using these two things as the ground truth, they adjust all the weights of this MLP2, which is just like MLP1, a multi-layer perceptron. That is, they have a certain number of hidden layers, all of which are fully connected, and so that's what they do. And so once all these models are trained using the normal purpose, then uh, so these are some of the like results which they are getting. So in this graph, the on the x-axis there is the ground observation, I mean the rain gauge observations, and on the y-axis there are the rain rates from the ground radar. So the ground radar has from its images using MLP1 we are now able to predict the spatial maps of the rainfall. So like we can see that there is a high degree of correlation with the rain gauges. And then in here we see the a similar measurement of the performance of the MLP2 model is also done. So here we along the x-axis we have the rain rates as obtained from the ground radars, and along the y-axis we have the rain rates obtained from the spaceborne radar, the TRMM radar. And so once again we see this kind of a almost near perfect correlation, which means that we have been able to do the predictions quite properly. Okay. So and so like so what we are able to get is like not only point wise of estimates, but we get as like a spatial map of the rainfall. So here each of the like if you look at these kind blue images, so here the values of the pixels actually stand for the rain rate. So like as this color bar shows, the different colors in the of the different pixels indicate different intensities of rainfall at the different locations. So now after this training has been done, you can say that you can see that the measurements are mostly consistent. That is this the what the MLP1 predicts from the that is what based on the ground radar, and what MLP2 predicts based on the spaceborne radar are almost coinciding. And they are also they can be both of them can be cross valid they both of them can be corroborated against the standard TRMM data product. So you can see there is reasonable so these two are nearly perfectly aligned to each other, and they are reasonably aligned with the standard TRMM observations, the TRMM measurements. Okay, so that's what this paper does in a nutshell. So it is it takes the rainfall measurements from different sources, the ground sources as well as the space sources, and is able to reconcile them to a to a mutually consistent value, which is also consistent with say more direct measurements, either from which may be either from the rain gauges or from the these the data products from TRMM. And so although they have done it from for although the network has been trained for one particular region, namely Florida, now they are showing that the same thing can be done throughout the world, at any place of the world, if they have sufficient these uh, sufficient observations from these radars. Okay, so that is what this paper is about. Now we come to a similar paper which also does something along very similar lines. So this is saying a machine learning system for precipitation estimation using satellite and ground radar network observations. Right. So last time we had two radars, one ground-based radars and one space-based TRMM radar. So now they are saying satellite and ground radar network observations. So coming to the abstract, space-based precipitation products are often used for regional and or global hydrologic modeling and climate studies. A number of precipitation products at multiple space and time scales have been developed based on satellite observations. However, their accuracy is limited due to the restrictions on spatiotemporal sampling of the satellite sensors and the applied parametric retrieval algorithms. These sensors which are mounted on the satellite, they will be taking their that is they will be sampling, or they will be taking their images or capturing the images at certain intervals. So so the spatial and temporal resolution may be limited. That is, by spatial resolution I mean the each side of a pixel, that is each pixel, how much region it actually covers. So the smaller that region is, we have seen, the more high resolution we can we consider it. And similarly, the time interval at which such images are taken. Uh, Now, similarly, ground-based weather radar is widely used for quantitative precipitation estimation, which they are calling as QPE, especially after the implementation of dual polarization capability and urban scale deployment of high resolution X-band radar networks. Now, ground-based radars are often used for the validation of various spaceborne measurements and products. So this is like this is already something we have seen in the previous paper. This article introduces a novel machine learning based data fusion framework to improve the satellite based precipitation retrievals by incorporating dual polarization measurements from a ground radar network. Right. So, last time they were using the ground radar net. They were considering the two data sources: ground radar network and the spaceborne radar. So, in this case, the ground radar network is still there. Instead of spaceborne network radar, they are using satellite-based precipitation retrievals. Now, in the prototype architecture of this fusion system is detailed. In particular, a deep learning multi-layer perceptron is designed to produce the rainfall estimates using the geostationary satellite infrared data and low Earth orbit satellite passive microwave based retrievals as inputs. So this time also they are following the same approach as the previous one. So these are the inputs to the multi-layer perceptron, that is the satellite imagery. The high quality rainfall products from the ground radar are used as target labels to train this MLP model. So in the previous paper, in case of MLP2, they had used this kind of a neural network to map the spaceborne radar estimates to the ground radar estimates. In this case, they are using the similar neural network to map the satellite estimates to the ground radar estimates. Okay. An urban scale demonstration study is done over the Dallas-Fort Worth Metroplex. In addition, the Climate Prediction Center morphing technique is adopted for pre-processing the satellite observations. Rainfall products from this deep learning system are evaluated using some standard products. The results show that the proposed data fusion framework can be used for generating accurate precipitation estimates and could be considered as an alternative tool for developing future satellite retrieval algorithms. Okay, so like you can see clear parallels between this paper and the previous paper. So we will not spend much time on this paper. Just uh, the schematic diagram here. So unlike the previous case where they had two multi-layer perceptrons, in this case they have only one. So the inputs are coming in from two sources. One is the geosatellite IR data, like which is of course like a set of infrared images, and then there is the like LEO satellite. So there are two satellites, Geo and LEO. Both of them are one is sending infrared data and the other is saying this like PMW data. So like you can say both are sets of imagery. The targets are the ground-based the dual polarization radar measurements. So from these, so we can assume, so although it is not mentioned in the paper, so we can assume that that is these radars have already been calibrated with the ground station observations using the MLP1 kind of model. So from these radars, we can now expect to get a like a uh, fairly accurate and high resolution estimate of the rainfall over a large region. So then there is this multi-layer perceptron model which takes the inputs from both the satellites and then produces the outputs, which is the improved precipitation estimation. Right. So there is less to be said about the nature of the neural network. It is just a multi-layer perceptron, means there are multiple hidden layers, all of which are fully connected. And so, yeah, so that is how the whole thing works. And once they have trained this once they have trained this thing, this perceptron, now it is able to utilize the satellite imagery from the geo and leo satellites to produce the accurate estimates of rainfall, like over the like over a large region. I mean, it's basically over any region over which from or over which these geo and leo satellites can capture the their imagery. Yes, so yeah, so this just demonstrates the radar network which they have, as well as the coverage. So as you can see, so the coverage of red, when we have a radar network, its coverage is important, so that every location in the or every target location is covered by at least one, but preferably by multiple radars, so that again so idea actually we can when we have multiple radars, then not all of them will be perfectly calibrated. So ideally again we can build some kind of a neural network, like the way, like what they have already done, to calibrate the that is to calibrate the estimates of one with another, so that we can get a consistent estimate. They have probably not gone into all that and so on. So yeah. Yeah, so this is the what they're it's some kind of a schematic diagram, and just like in the previous paper, so here they are basically showing the satellite, the spatial distributions of the rainfall, and that is each of these pixels here basically are spatial regions, and the pixel values indicate the rainfall intensities at the different places. So yeah, so this is with the these images, they is what they have got from the for one particular time period in 2015, and the next, and B is another one which I mean, yeah, sorry. Yeah, so these, like these are I guess yeah, so these are taken at different time intervals, and here you can see the difference between them. And yeah, so like once you have got the like you got this kind of an like got these kinds of products, so they basically give you some very high resolution estimates of the or I mean very high spatial resolution estimates of the rainfall. Now you like we can always do the spatial averaging and compare them to any data products with which you want to capture, with which you want to compare. So so some data products are already there, and so they so they use the technique of spatial resolution to bring both the sets of estimates. One is the one is what they have obtained from the neural network, and the other is what is this the CMOF technique which they already have. They like like both are brought to the same spatial resolution, and then they are compared like this and so on. Okay, so we'll not go further into this paper. Now let us come to an like another one, which this is also along similar lines. Just let it load. So this is a paper from IIT Kharagpur itself. So this paper, what it tries to do is it utilizes the like these satellite-based imagery to like estimate the groundwater level at different like across the like across a particular region. So Just a second. Yeah, let's see this view. So, so first of all, what are these the satellites? They are capable of measuring something known as an NDVI. So this is called the normalized difference vegetation index. So so there is a particular formula for NDVI. So what that is the satellites, they measure some like that is the, as I said, they measure images at different wavelengths. So like just a second. So like so they considered so this is the formula for NDVI. So there are there is like some wavelengths are known as NIR, and some are the red. So that is there is a visible range imagery, and there are the near infrared parts of the imagery that is called NIR. So you can say that NIR is like at any particular pixel, let us say I comma j, there is this NIR value obtained from the imagery taken at certain wavelengths, and then there is also the pixel values of red, which is take of of that is the pixels taken in the visible range. So let us just say that there are two images, I1 and I2. At so what they do is this NDVI is calculated by I1 as I1 minus I2 divided by I1 plus I2. That is the formula, and this calculation is done at per pixel level. So basically that way what is obtained in a like is said to be the normalized difference vegetation index. So so it is essentially a measure of the amount of greenness at a particular pixel. So the as I have said repeatedly, the when we are considering these kinds of remote sensing data or remote sensing imagery, every pixel actually corresponds to a spatial location. So if it like if a particular pixel, if obtained from the remote sensing imagery, has a higher component of greenness to it, that like that may suggest that the corresponding spatial location has a high degree of vegetation present in it, because we know the relation between greenness and vegetation. So this NDVI index, which is like calculated from the satellite imagery, it is basically used as an efficient indicator for vegetation cover. It's called considered as a proxy for vegetation cover. So like that is to say, these satellites are not actually measuring or calculating whether there is some vegetation present in that region. It is what it is measuring is basically the amount of greenness in the different pixels, and that greenness is being considered as a proxy for vegetation. Now of course it's not a durable or a very robust proxy, because greenness need not arise out of vegetation. It can arise from some other reasons also. Like say if a particular region has like has is somehow painted green, if a vast region is somehow painted green, that does not mean vegetation, but probably it will have a high NDVI index. So but anyways, so when we are considering so those are like exceptional cases, but in general we can assume that yeah, like if certain pixels are having a high degree of greenness, it may not be unreasonable to think that they contain vegetation. Now, here in this paper, we assess the possibility of using NDVI as an indicator of groundwater storage. So, this may be look a bit strange. That is, where is vegetation and where is this greenness of pixels and where is groundwater storage. So but then like it is generally understood that there soil scientists about the relationship between vegetation and groundwater. And since we cannot measure groundwater, sorry, vegetation directly, they are using measuring it as using the proxy of this NDVI. So now they are seeing if they can parameterize the relation between this vegetation and groundwater using some kind of a machine learning model. So or in other words, the general aim is they want to measure groundwater at levels at like over a large region, but of course they cannot do it like everywhere, because just like these rain gauges cannot be placed at every location, they can be placed only at a particular regions. So similarly for regarding groundwater also, they can get like groundwater can be measured where there are these deep wells or aquifers where they can actually where it is actually possible to measure the depth of groundwater. But then again, we don't have wells everywhere. So basically they have wells at some regions. Those wells, you can say, they provide the ground truth of the groundwater level, and using those like they need to, whatever estimates they are making, they need to calibrate with that ground truth so that they can get an like an accurate estimate over an entire region, including those particular points which have the wells. Now, we use groundwater level obtained from in situ groundwater observation wells in India during this period. What is in situ? In situ means like localized, highly localized observation. That is, if you have a well like in the backyard of your house, so that you can measure the depth of water in that well. So that will give you the depth of groundwater at precisely at that location, not in any other location in your neighborhood. So that is called an in situ estimate. Now, good correlation is observed between NDVI and GWL, means groundwater level, in natural vegetation covered areas, that is forest lands, shrubs and grasslands. We apply artificial neural network and support vector machines to investigate the relationship between GWL and NDVI using both the parameters as input. Okay. Next, artificial neural network and support vector machine simulated GWL matches very well with observed GWL, particularly in the naturally vegetated regions. They are able to that is this using the NDVI. So just like in the previous case, they were using the radar images to estimate the rainfall. Here, like the aim is to use this satellite imagery, or rather this NDVI imagery, to like estimate the groundwater. And this again is this kind of estimation is again done using either neural networks or support vector machines. Now, whatever they have estimated, they will compare with the in situ observations from the different ground wells. And what they claim to have found is that especially in the these vegetation, natural vegetation areas like forest lands, shrubs and grasslands, there is a very good like matching between what is predicted by the neural networks and what is observed from the wells. Thus, we interpret that NDVI may be used as a suitable indicator of groundwater storage conditions in certain areas where the water table is shallow and the vegetation is natural, and where in situ groundwater observations are not available. So, so like especially in those places where the ground where the water table is shallow, that is where the groundwater is not too deep, it is possible to estimate the depth from the satellite imagery. And if these groundwater observations are not available, then this this satellite-based groundwater measurement framework, this can make up for the absence of these in situ observations by predicting properly, by making very accurate predictions. Okay. So, methodologically, as far as the machine learning models are concerned, again, there is not much innovation in this paper. So there is they have used a standard neural network and a standard support vector machine. So just to give the context, this is the map of India, and these are where here they have shown the dense natural vegetation. So these are the regions where these are the places of I mean naturally forested regions where there are there is a high natural vegetation. So their claim is that in these regions or in these places, the estimate of the water table is particularly accurate. And this one, it basically it's showing the estimates of the water table depth, that is the groundwater level. It's shown at a pixel level. So this map is obtained from, uh, I am not sure whether this map B is obtained is like the result of the neural network which they have developed, or is it the ground truth which they have obtained from some other source. Uh, yeah, so here basically they are plotting the correlation between the this between the groundwater estimates which they have got from using their algorithm, and the in situ estimates which they have got. So here you may see that these red regions, these red pixels are the places where the correlation is the highest, that is their prediction is almost perfect. And so as they have claimed, these places where the correlation is highest are also the places of natural vegetation mostly, either along these forested regions of Madhya Pradesh, Odisha, Jharkhand, etc., and also along the western coast. So here we see a reasonably high correlation. While in the northern regions, say the upper Gangetic Plains, Punjab, etc., there the prediction is not so good. So the reason for that why the prediction is not so good in these regions, because there is a high groundwater fed irrigation. So these are the places where the agriculture uses a lot of groundwater. So so that is to say there is a lot of manual intervention. So yes, so the vegetation is there, that is these are the cultivated regions. So if you consider the NDVI, the NDVI will still be quite good, because not only they are for not only forest lands but also agricultural lands, they are green. So all these regions will have high value of NDVI. But here in these regions, the groundwater is actually being utilized to sustain the agriculture. So the more the agriculture happens, the less will be the groundwater. So that is why there is very less correlation between the in these regions between what is estimated through NDVI and what is the actual groundwater level. So that is the whole argument. So yeah, so here they're so they have taken two approaches. One is the artificial neural network approach. So there is really not much in this. This is not really such a very interesting model. So those of you who have been allotted a project in this topic, they will be encouraged to try a better neural network, or to see if if these results can be improved upon. So this is basically a feed forward network with 10 hidden layers. Like all the layers are the fully connected layers. So there is no convolution or pooling or anything involved here. So so basically the input is the NDVI and the output is the estimates of the groundwater levels. And similarly, an SVM, a support vector machine, is also trained for this purpose. So yeah, so this is what the paper is all about. So here they have shown at different locations how is like how good their prediction is. So here, like they have, especially for different types of regions, agriculture, forest, and shrubland, they have they have shown the correlation between between their uh, their uh, estimates as well as the the true measurements of groundwater level. So as this suggests, so you can see that in the agricultural lands, the correlation coefficient R is quite low, is very low, 0.11. Means that there is hardly any correlation between what they have estimated and the ground truth. But in the forested regions, the correlation coefficient is very high, R equal to 0.63. That's in earth science domain, that this is a it is very high, or at least fairly high correlation coefficient, which means that their estimates are generally agreeing with the ground truth. In the shrubland, it is R equal to 0.38, which is not great but decent. So just like I said a bit earlier, in places of agriculture, especially groundwater driven agriculture, there is very little correlation between NDVI and the groundwater level for reasons I already described. But this in forested or regions, this relation is quite strong. Similarly, in shrubland regions also it is reasonable. So based on this, they have done this study. So yeah, so basically that's all we have for today. So today we considered three papers, all of which are basically on this topic when we are using the remote sensing imagery as some kind of proxies to measure certain like certain earth system related variables. In these cases it was precipitation, in these cases it is groundwater level. So basically what is done is like the input is some kind of a remote sensing imagery over a particular region, and the output is a high resolution spatial map of what we are of the variable that we are trying to measure. And the input to output mapping is done using some kind of a machine learning model. So in all these three papers, we have seen basically a multi-layer neural network. uh, I am not sure why the authors here have not considered more sophisticated or other more advanced neural networks, like say the CNNs and so on. So some of you, if any are doing the project in this on this topic, you can actually try out CNNs and see if you can beat the results which these papers have reported using the multi-layer perceptron and so on. Okay. So with that, we come to the end of this class. And yeah, so those of you who still have not specified your seminar preferences must do that. I am indicating like I am confirming everyone's preferences or allotting the preferences by marking the one of their preferences in green color. So those of you who have already been allotted a project or a seminar must start working on it. So the seminar you should the seminar videos you should submit by the end of March, by March 31st. You should record the video that is of a video of approximately 20 to 25 minutes. Upload the link, upload those videos on YouTube, and share the links in a Excel sheet that will be provided. And regarding the second assignment whose deadline is approaching, you must submit it through Moodle. So in Moodle, we have created an assignment where you need to upload it. I will send out a detailed instruction. So with that, we'll stop today. So thank you, and we'll meet again next Monday. The next Monday's class will be again